All right, CNBT 1311, we're back, chapter 12-2 video, concrete. This chart just represents the water to cement ratio and the strength that you get. Um, so let's say we want 5,000 psi concrete for a type 1. This is your 28-day break strength. Then you want your water to cement ratio to be somewhere between here and here. Okay, this is super wet and this is dry. Now, your concrete people like to pour concrete as wet as they can because it'll flow. You get it too wet, the aggregate sinks, and so you need. Um, my rule of thumb was always to hit the midpoint. Um, always hit the midpoint. That gives you some wiggle room. If it gets a little too dry, you can add some more water to it. But you gotta watch your water to cement ratio. Um, the best thing to do is get it out of the truck and get it placed as quick as possible because that thing's hydrating in the truck. Water cement ratio is just literally what it is. It's the ratio of mixing water to the cement in a unit volume of a concrete mix, and expressed by weight as a decimal fraction or as gallons of water per sack of cement. Now, as an engineer, we had to do as a structural engineer, we had to come up with the concrete mix design. And we'd get with the ready mix people like Parker Brothers. They're no longer in business, but they were big. Parker Brothers owned all the barges to bring in the materials um, and the cement plants, and then the ready mix plants. Um, Parker Brothers were originally a bunch of tugboat captains. All right. According to Abrams' law, formulated by D.A. Abrams in 1919, the compressive strength of concrete is inversely proportional to the ratio of water to the cement. If too much water is used, the concrete mix will be weak and porous after curing. If too little water is used, the mix will be dense but difficult to place and work. For most applications, the water-cement ratio should range from 0.45 to 0.6. Okay, and your mileage will vary, and this is your engineer and your ready mix people's problem. It's yours if they screw it up. All right, concrete's normally specified according to the compressive strength it will develop in 28 days after placement. 7 days for high early strength concrete. So if you're doing a platform reinforced concrete structure, high rise, you may want to pay for the high early strength concrete and have your 7 day breaks equal a normal 28-day break. That way, you can pull the flying forms out, jack them up, put them in the next floor, and start laying your reinforcing and all the weight of the construction up there. Now, the slump test is very important. It's a method for determining the consistency and workability of freshly mixed concrete. It measuring the slump of a test specimen expressed as a vertical setting in inches. All right. Then the compressive test, a compression test, for determining the compressive strength of a concrete, is in a hydraulic press at the testing company, um, and to measure the maximum loaded test cylinder, um, which is 6 inches in diameter and 12 inches high. And there'll be a bunch of these. They'll cast a bunch of these specimens on pour, and if you've got multiple trucks, um, then they might do each truck. They'll do a slump test on each truck, but they might do compressive cylinders out of each truck or every 10 trucks. Because the last thing you want to have to do is come in and core your concrete um, to do a test cylinder. So that's why they do them on site as they're placing the um, concrete. All right. American Concrete Institute is ACI, the American Concrete Institute. They are the building code requirements for reinforced concrete. Every building code around the planet refers back to American Concrete Institute, the ACI. Okay. Now, your local building code may say, we don't care what your structural engineer thinks he can get away with. We want a minimum of 5,000 psi concrete for this occupancy type or whatever. Again, you got to check your codes. But the structural engineer and the concrete people, they live and die by the ACI code. I've got tons of these. And it's not just one code. They've got a code for everything. They got a code for mixes. They've got, you name it. All right. He's got a general reinforced slab up here. What does he say? 3/4 inch minimum for number 5 bars, and smaller. Oh, that's the spacing, the cover. Now, if this is a slab on grade, it's going to be 3 inches. But let's just say this is an elevated slab. You've got to watch that space. You've got to get that aggregate in there and around it and get it vibrated. 1.5 inch minimum when exposed to weather, which is, I don't think, it depends on what weather it's exposed to. If it's exposed to ground or water, it needs to be 3 inches. 2 inch for number 6 bars and larger. And for minimum coverage of steel reinforcement and other concrete members, you need to see 308 and spread footings. And we all know what that was. That was 3 inches if it's a footing on grade, right? Sewage treatment walls. Some of the digesters we held a 3 inch space. And of course we had larger aggregate. And the vertical bars were really heavy, and these were just tie bars. If this was a wall, you're looking down through a wall section. And if it was a wall, you'd have 2 rows of reinforcing steel. With another tie bar coming across it like that. Okay. All right. So once you do your slump test, this is what you're measuring right in here. This is what you're measuring. All right. So let's watch a fella do a honest to God slump test.
Is moist both inside and out. You want to perform this test on a flat, smooth, rigid surface, free of any vibration. And it needs to be a non-absorbent surface. The cone will be held in place. You can stand on the ears, or you can use the slump place and lock them into place. We'll fill the cone, 3 equal lifts by volume, rotating the concrete around the mouth of the cone to evenly distribute it. I'm going to rod this lift throughout its depth without forcibly striking the bottom. Half of my roddings are going to be at an angle to ensure that I get proper penetration into the corners. The rest will be across the cross section. Second lift. We'll fill the mold to 2/3 by volume. We'll rod this lift throughout its depth, penetrating the lift below by approximately 1 inch. Third and final lift, we'll completely fill the mold. We'll rod this lift throughout its depth, penetrating the lift below by approximately 1 inch. If at any time the concrete falls below the lip of the mold, you'll add a representative portion of concrete back into the mold and begin rodding where you left off. With a rolling, screeding action, you'll strike off the top of the mold. The tamping rod is the only approved method for striking off the mold. Remove any excess concrete. We're going to raise the mold in 5 ± 2 seconds, clearing the concrete slump by 12 inches. You don't want any torsion or side-to-side movement as you raise this mold. We'll invert the cone, measure down to the offset center.
That's wet concrete, man. That's some pretty wet
and
stuff.
get your reading for your slump.
All right. That that's how you do a slump. And the concrete that he was slumping, doing a slump test on, that stuff was pretty wet. You have charts through the ACI code that tells you what's a permissible slump. All right, let's down to reinforcing. Still reinforcing. All right, this is controlled by ACI and the Concrete Reinforcing Steel Institute, the CRSI handbook and standards. CRSI handbook and standards. I have my old CRSI handbooks, just like I do my American Concrete Institute codes. And in the CRSI handbook, they have details for retaining walls and what you need for a proper retaining wall with so much height of dirt, head of pressure on one side of the wall. So anyway, reinforcing bars are steel sections of hot rolled, just like structural steel is, with ribs and other deformations. These are in 1/8 inch increments, so a number 5 bar is 5/8 of an inch, okay, in diameter. Welded wire fabric consists of grid of wire bars that are welded together at all the points of the intersection. The fabric is typically used to provide temperature reinforcement for slabs, but the heavier gauges can also be used to reinforce concrete walls and roadways and slabs and stuff like that. The fabric is designed by size of the grid in inches, followed by a number indicating the wire gauge. For cross-sectional area, you can go back to chapter 3.18 if you really care. Okay. Now, you can get some heavy welded wire fabric. And ASHTO, the American which is a specification for highways and bridges, partner with ACI and the CRSI to come up with acceptable heavy fabrics for reinforced concrete highway slabs. All right, so bar size, number 3 is a 3/8, 4 is a 4/8 or 1/2 inch, 5/8, 6/8 is 3/4, so forth and so on. And a number 8 bar is 1 inch in diameter. That's 1 inch and 1/8, and that's 1 inch and 1/4. Number 10. All right. And these things are laid out on grids, and I showed you in another video the chairs that are used to keep this rebar off and get it where you want it in the concrete slab or wall. All right, let's move on. Masonry. In this section, he gives you the type of masonry, grades it. Common brick, face brick. Common brick is called your building brick. It's made of general building purposes and not specifically treated for color and texture. Okay. A face brick is made of special clays for facing a wall. It's often treated to produce the desired color and surface texture. And there are so many different types. If you go out to Acme Bricks website, Acme, we're not talking about a Roadrunner cartoon, but the Acme Brick Company. They've been around for a gazillion years. And you'll learn more about brick than you ever wanted to know. All right. You got brick types. The brick type designates the permissible variation in size and color and chippage and distortion on a face brick unit. FBX is a face brick suitable for use where minimum variation in size. FBS is a face brick suitable for use where a wider color range and greater variation in size are permitted. All right. And FBA is a face brick suitable for use where particular effects are desired, resulting from non-uniformity in size and color and texture of the individual units. So, so FBX is your most tightly controlled. This is lesser controlled, and this is random, lesser controlled. That doesn't mean it's crap brick. It just means that if you wanted a variation in texture and size and stuff like that for your brick. All right. Brick is a masonry unit of clay. All right. It's a masonry unit of clay. We've talked about that sun. While plastic and hardened by firing in a kiln, this is what we refer to as high fired or sun dried. Okay. Sun dried brick is not as strong as it fired in a kiln. They load the moist clay blocks, interlace them on a railroad car, and roll that puppy into a big oven, almost like a heat treating oven in a steel fabrication heat treating pressure vessels. Soft mud process refers to forming brick by molding relatively wet clay having a moisture content. Sand struck brick is formed in the soft mud process with a mold line with sand to prevent sticking and producing a matte textured surface. Water struck brick is formed in the soft mud process with a mold lubricated with water to prevent sticking, producing a smooth, dense surface. Now, why would you want a dense surface? Well, if you got a porous surface, then it's going to absorb more water from the environment, right? The rain. All right. All right. Now we have a stiff mud process as opposed to the soft mud process. These were soft mud. This is now we're getting into stiff mud. It refers to forming brick and structural tile by extruding stiff but plastic clay having a moisture content of 12% to 15%. And compare this moisture content of 12 to 15 to the 20 to 30 up here, and you'll see that this is going to be stiffer. It's going to left moisture in it. Okay, it's not as wet. Okay, and this is extruded through an extrusion process, just like extruded aluminum is. You heat that aluminum ingot up to about 800 degrees and hit it with a ram and push it through the die to make the fancy aluminum shapes. All right. After it goes through the die, it's wire cut and then stacked on a firing car to be rolled into the kiln. Dry press process refers to forming a brick by molding relatively dry clay having a moisture content of 5% to 7% under very high pressure, resulting in sharp-edged, smooth surface bricks and a lot more dense. And the density equates to its structural integrity. The denser it is, the less moisture that's in it before it goes into the kiln, makes a harder, stronger brick. Now, one's not necessarily better than the other. This is where you and your structural engineer will have to decide the cost factor. And as you can see, you can imagine this dry press process is going to be more expensive than, say, the soft mud process. Okay? All right. So compare your moisture densities, 5% to 7, 12% to 15, and then the wet process, what I call wet, it's the mud, soft mud, is 20% to 30%. All right. This is probably more than you ever wanted to know about brick. But seriously, if you're really interested in masonry, brick masonry, then go out to the Acme website. Um, Somewhere in my vast library and books in my past engineering life, I have a masonry engineer's handbook um, that was tied to one of the building code institutes. Um, it takes a little bit more engineering effort to do engineered masonry walls, as you might imagine, than it would be cast in place concrete. Um, Effervescence. This is something you got to worry about. It's a white powdery deposit that forms on an exposed masonry or concrete surface. Um, it's not just for masonry, it's also for concrete. And it's caused by the leaching and crystallization of soluble salts from within the material. Now, we're not using salt water to mix the cement, I told you that. But you do have natural salts in with the aggregates, the cement, the additives, um, and it's reducing moisture absorption is the best assurance against effervescence. You'll see effervescence on the inside of a reinforced concrete wall or a masonry wall that's got like well, especially on a concrete wall, like a parking garage that's below grade. And if you get some moisture, a lot of water behind that wall, it'll eventually mitigate through and create that effervescence on the surface, the inside surface. Um, it can be very unsightly. Let's say that you wanted a nice, um, what did Acme call that red? I think it was East Texas, North Texas red, high fired brick clay. Yeah, it was. It was like a brownish red. Um, and let's say you wanted that look on your building. And if you're not careful with the effervescence, then you'll get these white streaks appearing on your brick, and you'll have to go out there and pressure wash it or etch it or acid wash it with a very, very mild solution to try to get that effervescence off. Um, so you spend all the time and money to build this thing and to spec a good, pretty brick, and if you're not careful with the moisture content in the mortar, you'll start leaching uh, effervescent lines, little white streaks. Okay? All right. The actual dimension of brick units vary due to shrinkage during the manufacturing process. The normal dimensions given in the table below include the mortar joints, which vary from a 1/4 inch to a 1/2 inch. So here is a table for a rule of thumb of, and back in chapter 5, we had modular brick coursing and masonry bonds. And your masonry manuals and engineering manuals will help lay this out. Acme Brick used to sell a template for laying out modular courser brick back in the days where we actually had drafting tables that were like 4 by 8 feet, and there were C's of them, and you actually drew your drawing with a pencil or ink pen, and this was like, I know, this is back in Noah's day, all right, but that's where I started as an engineer. We didn't have AutoCAD yet, but now with AutoCAD and Revit, you don't have to draw each individual layer and course line. You just go over to your Revit template if you've designed your Revit menu properly, and you click a hamburger with cheese and put that, and then drag it over into your drawing and do your little clicky thing, and boom, magically you have your coursework all laid out. All right, brick grades. This is important. The brick grade designates the durability of a brick unit when exposed to weathering. The United States is divided into 3 weathering regions. severe, moderate, and negligible. All right, according to annual winter rainfall and the annual number of freezing cycle days. Brick is graded for use in each region according to compressive strength, maximum water absorption, and the maximum saturation coefficient. That's like a percolation test for an aseptic system. All right, maximum saturation coefficient. All right, ties back to the absorption stuff. You can learn all about this, like from Acme Brick, or a good brick manufacturer. SW is brick suitable for exposure to severe weathering. SW severe weathering. Okay, and it defines what that is in here. It should have a minimum compressive strength of 2,500 psi. MW, what do you think that might be? Oh, moderate weathering. Okay. As you, as when used above grade on surfaces, unlikely to be permeated with water in sub-freezing temperatures. The minimum compressive strength is 2,200 psi. NW is negligible weathering, as when used with the backup or in an interior masonry. Minimum compressive strength is 1,250, and we discussed this before with masonry, that you'd use this grade for maybe an indoor wall or planter or something like that. And of course, as a designer, you have to balance the cost of these. Maybe the cost is negligible between NW and MW, or maybe the cost is negligible when you consider the total life cycle cost of your masonry wall. So maybe you spend a little bit more on the upfront for a better material, and because the labor cost is going to be the same. All right. The allowable compressive stresses in masonry walls are much less than the values given here because the quality of the masonry units, mortar, and workmanship may vary. All right, you go back to chapter 5 and dig through for that table. But then again, your mileage is going to vary. So we're just talking about just the individual masonry unit. You take it to a testing lab and put it in that hydraulic press and blow it apart. But when you start putting these together in a wall system, you have this. Is it a cavity wall? Is it a solid wall? What are your ties doing with your mortar lines in here? And the variations. As tight as you may get, your mortar joints may vary. Okay, how deep did they rake them? There's a whole lot of stuff that goes involved in this. Your building codes will govern how these are done, and your structural engineer is your friend. Now we get into concrete masonry. Okay, CMUs. CMU, concrete masonry unit. These are not concrete blocks. Concrete block or concrete brick is a solid concrete cast unit you use for landscaping, and you can also use it for structural if you want. Get with your structural engineer. Where we at on time on this one? We're 28 minutes. Okay, fine, we'll get to this. All right, concrete masonry units. They're precast of Portland cement, fine aggregate in water, molded into various shapes. We've already seen the various shapes. I do believe this is a repeat from a previous chapter. Concrete blocks, incorrectly referred to as a cement block. Your CMU is a hollow concrete masonry unit. It gives you a lot of freedom. You use these as structural ties between your coursework. Of course, this is a stretcher block. Run reinforcing bars up through here and fill that full of structural grout. Or you can fill these things full of foam, pressure foam, depending on your deal. Okay. Let's see. If you're going to go to the expense of using CMU, I'd certainly use it as a structural unit, and then worry about your insulation, either on the whichever side you think's best. And you can surface spray closed cell foam on this stuff. And we talked about even dry stacking them and then coating them with an epoxy, fiber reinforced epoxy plaster. I still don't think that's as good as a mortar joint. You still need to run reinforcing bars up through here. If you're going to go to the expense of doing something like that, use this as a structural element. All right, we have a normal weight block, we got medium weight block, and you got lightweight block. Okay. And we're not going to go through all the different types. You can read this. Double corner, stretcher blocks, corner return blocks. Your masonry contractor, he's going to look at your plans and go, okay, we're going to need so many of these and so many of these and so many of these. And then if it's a big project, you're going to check the shop drawings. They'll submit the drawings. This is what we plan to use. This is what we plan to buy. And then you'll have to check those with your specifications and your plans. I don't think we've seen this before. This is a pilaster. It's a special CMU that is designed to make a pilaster. A simple one, a single one. And in some pilasters, you just use a regular block and build a big reinforced concrete column. And we've seen those before, okay? Sash or jam blocks, seal blocks, cap blocks, control joint blocks, sound absorbing masonry units. Here's a bond beam for a header. We've seen this before. Well, let's go over here and look at CMU grades. Grade N is a load-bearing concrete masonry unit. Okay, it's used for both above and below and exposed to moisture or weather. Grade N units have a compressive strength from 800 to 1500 psi. Grade S is a load-bearing concrete masonry unit, limited to use above grade in exterior walls with weather-protected coatings. Okay. With weather-protected coatings. All right, so the grade S needs a weather-protected coating, where theoretically a grade N does not necessarily need a weather-protected coating, although you would be foolish if you did not. All right. So you'd use a grade S in a wall that's not exposed to moisture or weather. And it makes sense. Look, here's a compressive strength of 600 to 1,000. So, means it's less dense, right? Okay. CMU types. I am almost sure that we crossed this bridge before when we talk about CMUs. Chapter 12 is kind of a repeat. Anyway, type 1 is a unit manufactured to a specified limit of moisture content in order to maximize the drying shrinking, which can cause. Type 2 is a concrete masonry unit not manufactured to a specified limit moisture content. So if you're going to use, if you're a structural engineer, if you want a reinforced CMU wall, then you're going to want a type 1, okay, masonry unit. And I don't care if it's below grade or above grade, I would look at a grade N, okay? Grade N in type 1. Concrete bricks, a solid rectangular course. Now here's a concrete brick, and there were a lot of houses in the 80s made out of, they called it Mexican brick, but I don't think it came from Mexico. It might have, I don't know. But they were just a dimensional masonry unit that was just made out of concrete instead of clay. They're usually identical in size to a modular clay brick, but also available in 12 inches. So some of these were really long. Concrete units have a compressive strength from 2,000 to 3,000 psi. And they used them a lot for brick veneer, okay? And you can use these for tie bricks. It gives you a different structural look. Screen blocks are used in tropical areas. You've probably seen these in some older houses. These were very popular down here in some areas of Houston back in the 50s and early 60s, where there'd be like a screen partition to break up the direct sunlight that's hitting the wall. So it'd be like screen walls and stuff like that. It does allow airflow. This is a faced block that has a special ceramic glazed or polished face. We talked about that before, Spectra glaze and industrial plants. When you come in, just hose the whole area down, hose the walls, and that sort of thing. All right, now we're getting into steel. Okay, and all right, yeah, we'll go through the steel. Steel, as we've talked about, energy, the energy it takes to make steel. This is all hot rolled steel. This stuff comes out as molten steel in a steel plant, and then these things are rolled. Big rollers. You can get on YouTube and you can search for how it's made. How is a wide flange hot rolled steel beam made? And just enjoy your YouTube trip. A lot of energy it takes. Okay. Same with hot rolled angles. Okay. Now this is an S shape, commonly referred to as an I-beam because it looks like an I. All right. This is a C channel or C shape. Okay. And this is a wide flange. Okay. This is an H shape. Okay. Because it looks like an H. You'll see a lot of these used in retaining walls. They'll drive these down, and then they'll put the retaining wall material in here, slide it down through between the flanges along the web. All right. S shapes are used a lot for overhead cranes, especially for an underhung crane. See the rollers tapered, and that would be your trolley. And I think I drew this before for another video. Maybe this will be a better drawing, I don't know. And there'd be a matching one of these on this side. You got a through bolt going through, and then your hoist mechanism, your chain hoist or whatever, be hung from that, and it runs up and down the S shape. All right, this is a WT. It's a structural T. Some of these are cut from a W shape. They'll go ahead and run a W shape out, a wide flange, and then just cut it. Or they can be hot rolled into that shape. But most of them are cut. That way they don't have to have a special rolling table. So they'll just make a wide flange and then run it over to the saw and then just plasma cut that, or with a CNC plasma cutter. That's computer numeric control. A structural tubing comes in all shapes and sizes and wall thickness weights. And you can square or rectangular. Let's see, structural tubing is just what it is. It's not pipe, it's structural tubing. Now, if you're using oil fill pipe, they have the API, American Petroleum Institute, specifications for oil fill pipe. This is structural stuff. And then you've got bars, square bars and round bars. Okay. And they don't have to be square, they can be flat, can be rectangular. Okay. And it comes in all shapes and sizes. Now, structural tubing and pipe usually comes in 21-foot lengths, and the flats come in 20-foot lengths. These can be super long. They can be welded and screwed together. I'm not welded, screwed together. They can be bolted together. or welding to make them longer. All right. Mild or soft steel is a low carbon steel containing this much carbon. This is not a material science course. Medium steel is carbon steel containing from 25% to 45% carbon. Most structural steel is medium carbon steel. We refer to it as A36. ASTM, American Society of Testing Materials. American Society for Testing Materials, A36, is the most common strength and grade. It has a yield point of 36,000 psi or 36 ksi. A kip is 1,000 pounds. You can get hard steel. It's got high carbon steel containing from 45% to 85% carbon. Spring steel is a high carbon steel containing 85% to 1.8% carbon. Okay. Now all of this is what's referred to as carbon steel. Carbon steel is unalloyed steel in which the residual elements such as carbon, manganese, phosphorus, sulfur, and silicon are controlled. Any increase in carbon content increases the strength and hardness of the steel, but reduces its ductility and weldability. All right. So the harder it gets, the less it will bend, and the more brittle it is. Your tool steels are very high carbon steels. All right. And I'll beg to differ with the unalloyed, because you can get a recipe, you can go to your steel mill and tinker with the amount of manganese, phosphorus, and sulfur to get the different grades of steel. But for the most part, we don't really call it an alloyed steel, okay? And he's right there. So, I mean, I'm getting off in engineering geek land is what I'm doing right now, and I apologize. All right. Anyway, alloy steel, true alloy steel refers to a carbon steel to which various elements such as chromium, cobalt, copper, manganese, molybdenum, nickel, tungsten, or vanadium have been added in a sufficient amount to obtain a particular physical or chemical properties. All right. Inconel, which is resistance to high heat, is an alloy steel. It's got a lot of nickel in it, and when you machine it, the chips come off like little razor blades. Very sharp, very hard. All right. Stainless steel contains a minimum of 12% chromium. Sometimes it has nickel in it, and manganese or molybdenum as an additional alloying elements, so as to be highly resistant to corrosion. Now, stainless steel is not stainless steel, is not stainless steel, is not stainless steel. You have martinistic stainless steels and you have ferritic stainless steels. Most of the stainless steels that you use in the marine industry are martinistic. All right, they're not ferritic. Ferritic is the iron, Fe, okay? But you have ferritic stainless steels, which gun barrels are made out of, rifle barrels are made out of, and it has more iron in it, and a magnet will stick to it. All right, but a martinistic does not. All right, so you can have all the different grades of stainless steel: 304, 316, 4 in the 400 range. You can drive yourself crazy, but again, this is not a material science class. And then you get weldable grades of stainless, like 316L. The L means that it's got some extra stuff mixed in with it that makes it easier to weld. All right. Now you cannot weld stainless like you can weld carbon steel. Stainless steel welding is usually done with TIG, although you can stick weld stainless. You got to be very, very careful with it. But most stainless is welded with a shielding gas of argon. Whereas MIG welding on carbon steel, we would use C25, 25% CO2 and 75% argon. And that's on a shielded gas. You can get flux core MIG welding, where the flux is on the inside of the wire, and but I've already gone past what this course would require. All right. High strength low alloy steel is a low carbon steel containing less than 2% alloys in a chemical composition. It is specifically developed for increased strength, ductility, and resistance to corrosion. ASTM A572 is the most common strength grade with a yield point of 50,000 psi. All right. And you can drive yourself nuts going through all the different grades of alloy steel. Weathering steel is a high strength, low alloy steel that forms an oxide coating when exposed to rain or moisture in the atmosphere. This coating adheres firmly to the base metal and protects it from further corrosion. Structures using weathering steel should be detailed to prevent the small amounts of oxide carried off by rainwater from staining adjoining materials. All right. Cor-Ten was a U.S. steel trade name for weathering steel. All right. Basically, the bottom line after reading all this stuff to you is this stuff rusts, and it's designed to rust to a certain mill thickness of rust, and then it quits rusting because then the rust protects it. A lot of highway bridges, some of the newer ones around here, are Cor-Ten, and and so it's a weathering steel. And you'll see the rust stains coming down the concrete support columns up on top. There's a little discoloration of the concrete, and that's what he's talking about down here, the oxide. All right, that's what rust is. It's ferrous oxide, FeO2. It's not chemistry course, but that's what rust is. It's iron oxide, and it gives you that nasty rust streaks on your other building materials if you're not careful with how the water runs off. All right, tungsten steel is an alloy steel containing 10% to 20% tungsten, and is for increased hardness and heat retention at high temperatures. Actually, heat resistance. And at high temperatures. All right. There are other ferrous metals used in building construction. That's cast iron. Cast iron, traditional cast iron, is hard and brittle. It's non-malleable. It won't bend. It contains 2% to 4.5% carbon. It's high carbon. It's brittle. And 0.5 to 3% silicon. And it's usually wet cast in a sand mold, and then either machined to make many building products such as piping, grating, ornamental work, etc., etc. Malleable cast iron or ductile iron has been annealed by transforming the carbon content into graphite or removing it completely. It is a cast. They spin cast this stuff in a ductile. Who was that big pipe company I visited years ago over in the South? Anyway, they made cast iron and ductile iron. A lot of sewer pipe used to be ductile iron, but PVC's gotten so cheap that and it's lighter weight. Wrought iron is just that. It's tough, malleable, relatively soft iron that is readily forged and welded, having a fibrous structure, containing approximately 0.2% carbon and a small amount of uniformly distributed slag. In the old cowboy movies where you see that blacksmith beating on that iron, that's wrought iron, okay? That's wrought iron. A lot of ornamental iron work is wrought iron. There's some people that make a good living producing wrought iron security doors over the main entrance doors of a house. You have galvanized iron, which is coated with zinc to prevent rust. Now, there's another process called galvalume, I gave y'all a video link to that. Um, the carbon steel tubes that hold up my back patio porch, they're galvalumed. It's a combination of galvanizing and aluminum coating. Um, uh, Galvanizing is, if you scratch the galvanized coating down to the base metal of iron, it'll rust. The Galvalume takes care of that. You can scratch through the outer coating of the galvanizing, and the aluminum coating over the iron the carbon steel, the A36 tubing, square tubing, um, will then still protect it from rusting. Um, there's a video on the benefits of galvanizing and Galvalume in the video link from the previous weeks. Assuming that's up, but you can research it. It's called Galvalume. Non-ferrous metals, they contain no iron. There's no ferrous. There's no iron in it. Has no iron. All right. Aluminum, copper, lead are non-ferrous metals, and they're commonly used in building construction. Aluminum's an interesting metal. It's a metal that doesn't know it's a metal. Aluminum likes to release electrons at a high rate of speed compared to other building materials. That's the reason you use powdered aluminum. Powdered aluminum is a reactive metal. It'll burn at a high rate, just like powdered titanium in a titanium fire. You use powdered aluminum in with your ammonium nitrate fertilizer, your 30-aught fertilizer, and a little nitromethane fuel to make your homemade C4. Gives it a bigger pop, bigger bang. Aluminum's ductile. Aluminum can be extruded or it can be hot drawn. Cold drawn aluminum, not hot drawn, cold drawn aluminum is a little stronger than just normal extruded aluminum. You can get on YouTube and you can look at a video, search it on aluminum extrusion. You'll see that stuff comes out of that extruder like spaghetti. And but these shapes, these are all shaped in a die. This is all pushed. They take those ingots, heat them up to about 800 degrees, and shove it through this with a ram. And this is a die, a metal die that makes this shape. All right. So aluminum is a ductile, malleable, silver white metallic element, and its natural resistance to corrosion is due to the transparent film of oxide that forms on its surface. And this oxide coating can be thickened to increase corrosion resistance by any electrical and chemical process known as anodizing. Your colored aluminum that's used in a lot of window frames and storefronts, that stuff's all been anodized. Aluminum will oxidize if it's left exposed. During the anodizing process, the naturally light reflective surface of aluminum can be dyed a number of colors, warm, bright colors. And you can do this yourself at home. You can make your own little anodizing tank. You can get on YouTube. There's a lot of people that simple little recipes with a battery charger, anode and cathode, and you can anodize your aluminum yourself. But care must be taken to insulate aluminum from contact with other metals to prevent galvanic action. It should also be isolated from alkaline materials such as wet concrete, mortar, and plaster. Now, that's easier said than done, but we're talking wet okay? Wet concrete. Because what will happen is the chemical action and the hydration with the concrete and the calcium carbonate will start to corrode the surface of the aluminum, make it look real nasty. Galvanic action, I talked about this when we talked about aluminum wiring, right? When we talked about aluminum wiring in the previous video, um, um, a lot of houses, to save money back in the 70s and 80s, the builders were switching over to um, aluminum wiring in the houses, and that's fine. Um, the size of the wire had to be a little bigger than copper, um, but the cost savings was significant that they would use aluminum wiring. But remember in the previous video, I said there's a dielectric paste that you would put on the aluminum wire before you put it into the breaker or wrapped it around the outlet plug, because it's different material. One's aluminum and one is not. And so they were having problems with galvanic action over the life cycle of that, where the connections would start to corrode, and then you get intermittent shorts. And so if you're using aluminum wiring, you needed to put that dielectric paste on it to keep that from happening. Aluminum is widely used in extruded and sheet forms. I've got an old 14-foot Lone Star I'm rebuilding. I've had that thing since I was 8 years old. And I'm 69. So, and it was a used boat when my dad bought it. And it's aluminum. And I'm putting a new transom in it and beating the dings out of it and having to re-rivet some of the stuff. And we'll talk about riveting later. Aluminum's used for everything, flashing, roofing, you name it, okay? And you can get some high-strength aluminum alloys in shapes similar to those of structural T. The aluminum sections may be welded, bonded, and are glued, or mechanically fastened. Inside one of the wastewater treatment plants, it was Southwest Wastewater Treatment Plant, the intake structure. I used a lot of structural aluminum for the grading, aluminum structural shapes like a W section. And why is that? Because even though it would oxide, maybe a little oxide coating, it's not going to rust through like if you put a bunch of carbon steel in there. That would have to be painted, okay, or elastomerically coated. And it worked out real well. Plus, it's light. Now, aluminum is lighter than structural steel, so let's just say, and y'all don't care about this, but I'm going to tell you anyway, I don't care. Let's say you needed a 12-inch carbon steel W shape for a given load, X load. All right, and for the same span with aluminum, that thing might have to be 18 inches. Because aluminum basically weighs a third of steel, right? So that might have to be 18 inches if it's aluminum. If this is A36, if this is A36 material, and this is aluminum, and that depends on the grade of aluminum, okay? Aluminium, okay, all right. And if you really want to know how aluminum's made, there's a big aluminum plant down near Rockport as you're going in. Use bauxite, and they mix it up in a big cauldron, and you can get on YouTube and say, how is aluminum made? If you care. All right, copper. Copper is a ductile, malleable, metallic element that's widely used for electrical wiring. It is the best electrical wiring, in my opinion, Uh, it water piping, yeah, but with the new PEX that we have now, I would grade if I was going to replumb my house, it'd be with PEX. The only problem with PEX is if you've got rodent issues, they might like to chew on it, but you can shield it and insulate it. Copper's been used for years as flashing. Um, um, in the manufacture of alloys, bronze and brass have copper in it. Its color and resistance to corrosion also make it an excellent roofing and flashing material. It's expensive, very expensive. However, copper will corrode aluminum, steel, stainless steel, and zinc. You get them together, you're going to have an exchange of electrons between those different materials, and it will corrode. Now, copper does have a nice patina to it. It means the patina means that over the period of the life cycle of the copper, it'll change colors a little bit to like this greenish patina kind of thing. Um, um, and copper can be fastened, attached, supported only with copper or carefully selected brass fittings. Con, uh, Contact with red cedar in the presence of moisture will cause premature deterioration of the copper. The acids in the cedar um, will corrode the copper. You'll have an electron exchange again. Okay, you can solder copper, um, so um, just like you can copper piping, water piping, sweat it. Um, Brass refers to any various alloys consisting essentially of copper and zinc. Um, uh, Brass is used for windows, railings, trim, finish hardware, hinges, door handles. Um, Alloys that are brass, by definition, may have names that include the word bronze as architectural bronze. Okay, there's a difference between bronze and brass. Um, old Greek war helmets from the Bronze Age. Um, um, bronze is not as strong as brass. All right, but it was easier to manufacture back then. All right, brass is a really neat thing to machine. As a machinist, I take a brass valve stem and go out and play with it on my metal lathe sometimes because it's just it cuts on a lathe almost as good as high density polyethylene. It tends to be self-lubricating and it machines really smooth. Now there's different grades of brass. Um, there's a marine grade brass and normal utility grade brass, but that's outside the scope and course of this deal. All right, lead is a heavy. If this is a 16-week course, y'all be hating me face to face because I'd go off into material geek land. Lead is a heavy, soft, malleable, bluish gray metallic element used for flashing, sound isolation, and radiation shielding. Radiation shielding. Oh no! All right. Um, those aprons that they put on you when they do the X-rays. Of course, at my age, I kind of laugh. Why are you doing that? Well, we don't want you to get sterile. I said, I'm 69 years old. What do I care? But anyway, that's an H. I'm going to go to HR prison for that. Um, um, anyway, although lead is the heaviest of common metals, its pliability makes it desirable for application over uneven surfaces. Lead dust and vapors are extremely toxic. Lead dust and vapors are extremely toxic. So the term mad as a hatter, those old beaver hats, those old hatters, um, they would uh, shape and smooth the hat with mercury vapor heated up in a beaker, and the vapor fumes would drive them crazy after a while. So the term mad as a hatter is where that comes from. All right, because the vapors would make them go crazy. Galvanic action. This is what we're talking about up here. You get different materials together and you run the risk of having a galvanic action. Galvanic action can occur between two dissimilar metals when enough moisture is present for an electric current to flow. Electric current? You mean we're running electricity through this? Well, we're talking about the molecular electric, okay? This electric current will tend to corrode one metal while plating the other one. That's how anodizing works. You get on YouTube and look at a homemade anodizing thing, and you'll see the galvanic action between these two. But we're talking microscopic galvanic actions where one is exchanging electrons with the other. And the severity of the galvanic action depends on how far apart the two metals are on the galvanic series tables. And oh my God, here we go. Here's the galvanic series table. Here's the galvanic series table. Oh my God, we're over an hour. That's fine. We'll finish this off and go to another video. Okie dokie. All right, so we got gold and platinum up here. It's the most noble. That's your cathode. And your anode is down here, your least noble. Okay, so you got anodes and cathodes. And the galvanic series lists metals in order from most noble to least noble. Noble metals such as gold and silver resist oxidation when heated in air in solution by inorganic acids. The metal that's lower in the list is sacrificial and corrodes when enough moisture is present for an electric current to flow. The further apart the two metals are on the list, the more susceptible the least noble one is to corrosive deterioration. All right, so magnesium and zinc, look where copper's at. Copper and bronze, copper and stainless steel. All right, aluminum's way down here. Okay, so one's going to give up electrons and one's going to take the electrons. And that's where the corrosion comes from. Don't get all freaked out over all this stuff. All right. So, anyhow, all right. I think we'll stop here, and we will do 12. This will be 12:3. Man, we're only at 10 pages. Good God. Well, it's the last chapter, except for the appendix. The appendix in this book has got a lot of good stuff in it. That's why you need to keep this book. I'm telling you, for the rest of your little design life. All right.